Good evening to all of you. Hope my voice is audible to all. Today, thank you. So today we are going to discuss about how optimization, that means gradient descent algorithm based optimization techniques, will help a machine learning model to learn based on the available data. Fine. So as I said initially, when a kid joins the school, the available alphabets are like a data, his brain like a model, and how the brain will learn the data alphabets based on the approach followed by the school. That approach followed by the school is similar to the optimization technique. So in today's class, we are going to discuss about how a machine learning model will learn based on available data using a stochastic gradient descent optimization technique. Fine. Now, before going to the step-by-step procedure of how stochastic gradient descent optimization technique will help the machine learning model to learn, just first we will discuss how we can correlate the learning process of a machine learning model with optimization problem. Because I told that I am using I am using optimization technique to help the machine learning model to learn. Now, what is the correlation between the learning process of machine learning model with respect to the optimization technique? How we correlate these two? I will explain first, later we will slowly move into the algorithm. So for that, in order to explain all the optimization techniques, I am taking a simple linear regression. That is the one of the machine learning model I have considered. Fine? Good. So, what? Yeah, 1 minute. Yeah. Fine. So first we will discuss about simple linear regression model. First we will discuss about this regression model. Later we will discuss how we will correlate the learning process of simple linear regression model with respect to the optimization technique. So what is the simple linear regression model? So simple linear regression model is one of the machine learning model which help to predict some variable based on one input variable. You have to observe my statement, that is a simple linear regression model is one of the machine learning model which is used to predict a particular variable based on one input variable. That means only one input, one output, and you are going to estimate an output based on the available input. For example, suppose I want to predict load on a substation at time t. I want to estimate load on a substation at time t based on the load on the same substation previous day of the same time. That means 24 hours back. Then if this is the problem, then we can solve this problem by using the simple linear regression model, because we have the one input. That input is the load available on the previous day at that time. Now I want to going to estimate the load at the time t. That means, example I am telling in which type of applications we can use a simple linear regression model. Suppose if I want to predict load on a substation tomorrow at 6 a.m. based on the load at the same substation today at 6 a.m. So today at 6 a.m. load data is available. Based on that load data, I am going to estimate what will be the load on the same substation tomorrow at 6 a.m. That means one input, that is the load on the substation at 6 a.m. today, and one output, that is the load on the substation 6 a.m. tomorrow. That is the example for the simple linear regression model, one input and one output. You are going to estimate one output based on the one input. So for such type of problems, you can use the simple linear regression model. Fine. Now, so now we understood that simple linear regression model generally used to estimate a particular output based on a particular single input, right? So now machine learning model is available, right? So for the machine learning model, so like a kid brain is available. At the same time, if you want to learn, the information is required. That is like alphabets. Similarly, the regression model is available. Now I want to train this model. To forecast the load at a particular hour of the day based on the load at the same time but the previous day. So if that is a problem, I require the information. That means what the information required? That's called data. So data is X, that's the input, and Y is the output. So you have the multiple number of samples. Like let's assume actually I am going to estimate the load at 6 a.m. tomorrow based on the available load at 6 a.m. today. Today means it is a 25/11, right? So if this is a problem now first of all I want to train this model or make this model to learn based on some historical data, previous data. So the data must be containing like load data 6 a.m. today, you take that as a one output. So you are going to predict by using the load data 6 a.m. yesterday, that is called 24/11. So both data are available now to train this model, because today 6 a.m. is available and day before that means yesterday's 6 a.m. also available. So that is the one sample. Similarly 5 a.m. of today and 5 a.m. of yesterday, that is called 24. Like that you have to prepare the data. So the data contains only two columns, one column related to the output, another column related to the input. One column related to the output and another column related to the input. So let us assume, so we have a data which have the two columns X and Y represent YIA, I am telling that is the actual value. XIA, that is the actual input value, and I represent the sample number. So first sample, second sample, third sample, fourth sample, fifth sample, like that, historical data, right? Now, so how this, what is the simple linear regression model, what it is doing, now we will discuss, right? So now, let us assume this is the Y or YIA and this is the XIA. So based on this input X, I am going to estimate the output Y, right? So data points are available now. Let us assume some data points are available. So some data points are available like, so some data points are available. So that means what is the data points means, at particular value of X, this is the Y. At particular values of X, this is the Y. And this particular value of X, this is the Y. At this particular value of X, this is the Y. So these are based on samples, like suppose X and Y, let us assume 1, 5, 2, 4, like that. So then we can represent every point in the two-dimensional space. So these are the data points. So data point nothing but the available samples in the data set. Just I marked on the two-dimensional space. Now what the simple linear regression model is doing is, the simple linear regression model trying to find a straight line which has the minimum distance from all the data points. Like what I want to tell you is, so simple linear regression model is nothing but a linear line equation like this. which has the, so these are the data points, let us assume. So which has the minimum distance, from the each data point, So your simple linear regression model will be like this. Suppose if it is a simple linear regression model, SLR. Now this simple linear regression model will take input xia and it will predict based on the line equation. So this line equation will be like this: y equal to mxia plus c, right? The line equation, straight line equation, yia. So xia is the input. Now we have to multiply with a slope model parameter called m, and for this you have to add another model parameter c, then it will give you output yia. So this is the black box now. This is the simple linear regression model where we need to identify the m slope and c, so that for a given input the output will be predicted properly, right? So in the simple linear regression model is nothing but you have to identify a line equation which has the minimum distance from all the data points, right? Suppose, for example, I am telling, suppose y equal to 2x plus 3, let us assume, right? So then the data points will be when x equal to 1, y equal to 5, and x equal to 2 and y equal to 7. So then 1, 5, 2, 7, right? So you have, suppose, so I am going in the reverse side. Now these are the data points. Now I have to find a line which is passing through or which has a minimum distance from the data points. That means finally you have to identify m equal to 2 and c equal to 3. These are things you have to find. You have to identify the model parameters during the learning process. So for which values of m and c, most of the points are the line will be passing through the most of the data points. At the same time, it has the minimum distance from all the data points. So these data points are called as the actual values, and the points on the line will represent the predicted value. That means, suppose if this is the input, for this input, this point is the actual output yia, and this point will be the predicted output yip. So this distance is called as the error. So if this distance is less, then that means your model will predicting properly. If the distance, that error is more, then means your simple linear regression model is not properly predicting. I hope you understand, right? So I will explain this thing again in a different manner in the new sheet. So it is the y and this is the x. Fine. So let us assume. So this is the line which represents your simple linear regression model, yia equal to m into xia plus c. So for xia, suppose let us assume this is the x1a. For x1a, then this point is called, if you replace x1a in this equation, then m into x1a plus c, this value represents the predicted output. This is called predicted output yip. But in the data set what we have used, that is called xia and yia. So in the data set we are considered some values, right? Some values. So corresponding value available here I am placing here as a data point. So this is called as the distance or error. This distance must be minimum. If you have suppose if you take another input like x2a, for x2a this is the predicted output. Let us assume this is the actual output, then this is called as the error, right? So what the machine learning model, what the simple linear regression model will do during the learning process is, it is trying to identify a line equation which has a minimum distance or average minimum distance from all the data points. Average minimum distance from all the data points. Average minimum distance, it will trying to minimize the distance between the predicted output and actual output. So like that line will be shuffled. The line will be shuffled and finally it comes to one position where the error or the mean distance from the actual output and predicted output for all the data points will be minimum, right? So friends, see, so what is the distance between these two? Now what is the difference or distance between these two? So this point is called as actual output, YIA, and this point is called as predicted output, YIP. So YIP from the regression model. So simply regression model is called as I said, right? So regression model, it contains m parameter, model parameter is m, another model parameter is c, and it is a summation, and we are giving the input xia, and it will give from output YIP to predict the output, and it is a plus and it is also plus. So m into xia plus c equal to YIP. So during the learning process, what happened is, it is trying to find a suitable m and a suitable c such that the distance between the actual value and the predicted value, and actual value will be minimum. Right? Now tell me, what is the distance between these 2 points? This is the actual point and this is the predicted point. So what is the error, or what is the difference, or what is the distance between these two? What is the distance between these two, or difference between these 2 points? What is the difference between the actual value and predicted value? Anyone, please? Anyone able to tell? So what is the difference between the actual value which you have coming from the data set, predicted value which is coming from your simple linear regression model? Now what is the difference, or what is the distance between the actual value and the predicted value? It is a YIA and it is a YIP. Cheppanam. Hello?
YIA minus YIP.
Perfect. So that the difference or distance between these two is called the YIA minus YIP. Right? Now I can call, see, okay, YIA minus YIP. Now we are not calculating the learning algorithm will trying to minimize the distance between the actual value and can you keep in mute? Someone can keep in mute, please. Yeah. So during the learning process, what is doing is, we are trying to identify a line which has the minimum distance from all the data points, which has the minimum distance by considering all the data points. So I have considered only ith sample. I have in the data set, I have the thousands of samples, but I have the ith sample only. But I want to minimize the total distance. among all the samples, among all the samples here. Right? Then what, if you consider all the samples, then what will be the total error, or what is the total difference between the actual data points and predicted data points? Anyone can tell what is the equation we can write here? Yeah. So my question is, I have written this difference equation, that is the difference between the actual value, predicted value, by considering the only ith sample, only one sample. But what I want to do is, actually what happened is, we are trying to identify a line which has the minimum distance when we are comparing all the data points. With respect to all the data points, the difference between the predicted value, that means line equation, and actual value, that the data point will be minimum. The difference will be minimum when comparing all the samples. Then what is the slight modification we have to do here?
Sigma YIA minus YIP.
Perfect. So we have to use a term called sigma from I equal to 1 to n. N is called number of samples available in the data set. So it will give the total difference between the actual value and predicted value when we consider all the samples. So this is the total error. It's called a total error. Right? Now, still some modification I am doing here. See, what is that is fine. So this is the total distance, right? Now see, if I want to minimize this function, we can't use this function as it is, because sometimes YA may be more and YPB will be less. Then it will be positive. Let us assume, friends, I am telling, for I equal to 1, let us assume Y1A actual value equal to 4 and Y1P equal to 3, right? And for second sample I equal to 2, let us assume the actual value equal to 5 and predicted value equal to 6. Now what will be the error now? What is the error? Let us assume we are taking the only 2 samples. Let us assume your data set has only 2 samples. Then what will be the error? So that's equal to sigma equal to 1 to 2. That's called Y1A minus Y1P plus Y2A minus Y2P. So Y1A minus Y1P means 4 minus 3 plus Y2A minus Y2P means 5 minus 6. That's called 5 minus 6. Now what is the value? It is a 1 and it is a minus 1. That's equal to 0. It shows that error equal to 0. There is no difference between the actual value and the final value, predicted value for the given data set. Is it true? No. There is an error, right? But it is showing that 0. So to avoid that problem, I am considering a square term here. If you consider a square term here, what happened? Here it is a square, here it is a square, and here it is a square, here it is a square. Then it is a 1 square plus minus 1 square. That is the 1 plus 1, that's equal to 2. Total error. Hope you understand, right? So I am taking the small modification here, that is called I am taking the square term. I am taking the square term. Now I am, see, if we add, suppose actually in our data set we have thousands of samples. In our data set we have the thousands of samples. If you calculate the difference between the actual value and predicted value and make a square of it, and if you add all the 1000 samples, then there may be a possibility of not a number error. That means you are getting a huge large number sometimes. So to avoid that one, instead of taking the square error directly, I am doing small correction here, that is called multiplying the term with 1 by n. I am taking the 1 by n. Now it is called as దీన్ని మీరు కరెక్ట్గా చేస్తే this is the square and sum of square divided by total number of samples. So we can call it as a, if you are not using 1 by n, I want to call it as a square error, because I am calculating the error, I am making it the square, and I am adding for all the samples, so it is called as a square error. But when I am doing by 1 by n, then it is called as, maybe some people who attend the deep learning course, they can respond, they may know, it's called as MSE. So it's called as mean square error. So this error we need to minimize. That means if you are trying to minimize mean square error, is nothing but you are trying to minimize the difference between these two. So difference between these two means you are trying to find the m and c values where you get the minimum difference between these two. Then that happens. That's what we require. Means we have to train a machine learning model so that it will predict approximately equal to the what actual value is there. So if that is exists, then the difference between the actual value and predicted value will be very small. How we achieve that small difference? By minimizing the mean square error. Understood, right? So I think now you have an idea. So what is the purpose of optimization technique in the learning process? So what happened in the learning process of a simple linear regression model is, so the learning process of a simple linear regression model, not a simple linear regression model, any machine learning model, is minimization of the mean square error. So that is the objective. Any learning algorithm main objective is it is trying to minimize the mean square error. That mean square error will directly represent the difference between the actual output value and your predicted output value. So during the training, if the difference between the two are almost zero, or both actual value and predicted value is almost equal, then we can say that the given model is properly trained. Right? So now I hope you all understood, right? So now I can correlate that learning process of a machine learning model. Learning process of machine learning model is correlating with your optimization problem what we discussed yesterday. So in an optimization problem we required what we required? An objective function. So in the learning process of a simple linear regression model has an objective function. So what is that objective function? So I have to minimize the mean square error. So minimization of the mean square error of a simple linear regression model is an objective function. That's why, because of that reason, I am telling that the learning process of a machine learning model, I want to correlate, I can say that it is an optimization problem. Right? So now we are again moving from the machine learning aspect to again coming to the optimization problem aspect. Right? So what is the goal is? You have to minimize. So what is the main goal of any learning algorithm is minimize the mean square error that's equal to 1 by n sigma I equal to 1 to n actual value yia minus what is the yip? Anyone can tell? So that's the predicted value. What is the predicted value? So I will write in the next board. So during the learning process of a simple linear regression model, we are trying to minimize the mean square error that's equal to 1 by n sigma I equal to 1 to n yia minus yip whole square. So this is the objective. So because of that reason, we are calling this one as a optimization problem. So if it is an optimization problem, we required an optimization technique to solve this problem, to identify the minimum mean square error and also to identify the decision variables at which we get the minimum mean square error. Now my question is, what is the decision variable? What is the decision variable in this optimization problem or in the learning algorithm of simple linear regression model? Anyone can just have a thought, can tell me what may be the decision variable for this optimization problem. Yesterday we discussed, right, minimize 6x plus 4y something, and I said that x and y are the decision variables. And here what are the decision variables? Decision variables means we have to find the value of those variables at which we get the minimum objective function.
M and C.
What?
M and C.
Perfect.
YI.
Perfect. So that's equal to 1 by n sigma I equal to 1 to n yia. So yip means, so in the previous board I have written yip equal to m into xip plus c. So just I replace here in place of yip, that's equal to minus mxia minus, not is a input, input value no need to predict, right? We are giving the input and we have to predict the output. So mxia minus c whole square. Now our decision variables based on which your objective function will depend. So the decision variables are m and c, are we can call as model parameters of simple linear regression model. These m and c are called as a model parameters of simple linear regression model. So during the training process, at end we are identify a proper value of m and c at which that error will be minimum. The error will be minimum or almost equal to 0. If that is a 0, then that means error is 0 means the difference between the actual value and the predicted value will be almost 0, and actual value and predicted value are almost equal. Right? I hope you understand, right? Fine. So finally, your objective function, your loss function, your objective function are also called as a cost function. It is also called as a cost function in the machine learning terminology. It is also called as a loss function. In our optimization terminology, we are called as objective function. Right? Hope you understand. So that's why I am correlating this optimization problem. Sorry, it is a machine learning problem. The learning process of a machine learning model with optimization problem. Fine. Now, see. Now tell me another small discussion. Now we come to know that the learning process of a machine learning model is an optimization problem, because in the learning process of a machine learning model we are trying to minimize the mean square error. So it is a minimization of a particular objective. So it is a optimization problem. Now tell me friends, it is a linear optimization problem or non-linear optimization problem? It is a linear optimization problem or non-linear optimization problem?
Non-linear.
Yes, it comes as a non-linear optimization problem. Why it is a non-linear optimization problem? Your objective function is non-linear nature of your decision variables m and c. You can see a square term here. So it is a non-linear nature of your decision variables m and c because of the square term. So it is a non-linear nature. At the same time, it is a convex function. You have to observe it is a m square something and c square something. It is like a convex function. It's like a convex function. Like you have one bottom point. So due to that reason, we are starting with the gradient descent approaches. So gradient descent algorithm is used to solve the non-linear optimization problem, which is in the form of the convex function. Object function is in the form of the convex function. I hope you understand, right? So in the learning algorithm, so I'm trying to summarize everything once again. If we have a simple linear regression model and want to train that model to predict an output based on a single input properly, then you have to train it. So training of a model or learning process of a model is nothing but the minimization of that error, mean square error, which represents the difference between the actual input and actual output and predicted output. So because of that reason, we can correlate the learning process of a machine learning model is similar to your optimization problem. Now, in our optimization problem, you have an objective function. That objective function is mean square error, that's equal to 1 by n, sigma I equal to 1 to n, yia m into xia minus c whole square. That is in case of the simple linear regression model. If your model complexity increases, then the number of parameters will be increases. It is a simple linear regression model have the only two model parameters, one is the m, another is the c. If you go with the multiple linear regression model, then the number of parameters in the model also increases. If you go to the ANN, then the number of parameters will be more. If you go with the CNN, that is the number of parameters will be further more. But this the main goal of this course is in order to know how the optimization algorithm will help the model to learn, I am taking the very small simple model that is called simple linear regression model, where we can do our hand calculations also, and we can see the output also easily. Fine. So I hope you are ready now. So learning of a simple linear regression model is nothing but the minimization of your mean square error. Now we will discuss about a simple stochastic gradient descent optimization technique, and how it will help the simple linear regression model to learn or to update the model parameters M and C. We will discuss that procedure step by step. Moreover, there is a small correction I want to take here. You can take mean square error also, not an issue. You can take mean square error also, not an issue. But in the demonstration purpose, I am taking the off mean square error. So you are minimizing the off mean square error is nothing but similar to the minimization of the mean square error. But I am taking small modification. Off mean square error means 1 by 2 into 1 by n into sigma I equal to 1 to n yia minus m into xia minus c whole square. So why I am taking the off here is, see, we are using the gradient descent approaches. So in the gradient descent algorithm, what we are doing, trying to recollect yesterday in the gradient descent algorithm, first thing what we are doing is we are trying to calculate the derivative of a objective function with respect to the descent variable, right? So here our objective function is this one. If you make a differentiation, if you calculate the differentiation of this loss function with respect to the model parameter, then once you do the differentiation, then these 2 will becomes here, right? At the time of differentiation, the 2 will become forward, like x square equal to 2 into x, right? The 2 will becomes forward. So if there is no 1 by 2, you are making 2 into something, so it may cause the large step length. It may cause the large step length. So to avoid that one, to cancel that 2 and 2, just I am adding the 1 by 2. So then it is called as a off mean square error. But there is no issue if you take the MSE also, but in the numerical calculations, I am considering the off mean square error. So if you are trying to minimize the off mean square error is nothing but indirectly you are trying to minimize this term. So this term will reflect the mean square error. Fine. So now I want to discuss with you the first optimization method, stochastic gradient descent. See, all the optimizers which I am discussing from today, all are came from the roots of gradient descent optimization technique with small modifications. That's it. So what are those modifications? We are discussing one by one. We are discussing one by one. But in the first case, we are discussing about the stochastic gradient descent optimization. Now I will tell you how it will work. How it will work. Fine. So first what we have to do is step one. So we have a simple linear regression model. So if you have a simple linear regression model, if you want to train that simple linear regression model, you required a data. So data is a x and y. So one output and one input. So you have to read the data. Read the data x and y. So this containing a different number of samples. That depends upon this size. I want to call it as a xia and yia. So the data xia and yia. That's called data. Okay, fine. And next what we have to do is, in stochastic gradient descent optimization method, what is doing is, I will, before going to that algorithm, I will explain one more visualization aspect. In stochastic gradient descent optimization, we have to randomly choose initial values. Yesterday problem, we are trying to minimize f of x equal to x square plus 5. So what is the first step there? We are randomly initialize the x value. That's the descent variable. So here also you have to randomly initialize your descent variables. You have to randomly initialize your descent variables. Right? So what are the descent variables? for our problem, for a simple linear regression model, the decision variables are m and c. So you have to initialize the m and c. Let's assume I am initializing m equal to 1. So you have to randomly initialize. But I am explaining for the numerical calculations. I am taking the m equal to 1 and c equal to minus 1. M equal to 1 and c equal to minus 1. So you have to randomly initialize. Okay. So m equal to 1 and c equal to minus 1 means then your line will be like this, right? Your line will be like this. So it will represent the mx plus c, that's equal to 1 into x plus c, that's equal to minus 1. That's the line equation now. So it is the line position will be here. Line position will be here. Now what we are doing? Now call your sample. You have to call the first sample. Then what you doing? Let us assume the first sample is 1 and 5. Let us assume your first sample is 1 and 5. That means for x equal to 1, you have the y equal to 5. For x equal to 1, for input 1, you have the output 5. So that is somewhere else here, right? Now your gradient descent algorithm, so you have to take one sample at a time. I am taking the only one sample at a time. Now you have to update your m and c values. Once you are updating your m and c values, then this line will be trying to move towards the data point. Somewhere else it will be landed. Now I am updating with respect to the first data point. Now it moves to the here at this point. Now pass the second sample. Let us assume it is the 2 and 2. Let us assume 2 and 2. Now 2 and 2 means it is the 2. Some 2 means here. Let us use 2. Now what happened now? Now again you have to update m and c parameters. So it have to move in between these two somewhere here. M will be updated. Like that your line will be shuffled when you are updating the m and c values, and finally it will place at a particular point. Where the difference between the actual values onto the line, from the data points onto the line, the distance from the data points onto the line means that the predicted values onto the line will be minimum. That is the difference from the initial point, that actual points onto the line will be minimum. So this is called as it's a predicted value, this is the actual value, this is the predicted value, this is the actual value. So the difference will be minimum, there it will be stop. Right? So like that the line will be updated. How the line will be updated in case of the stochastic gradient algorithm means, in case of the stochastic gradient descent algorithm, you have to take one sample at a time, update your model parameters. Take second sample, update your model parameters. Take third sample, update your model parameters. You have to do it repeatedly for all samples, sample by sample. Understood? Let us assume your data set has 4 samples. Then what you have to do is you have to initialize model parameters m and c. Now take the first sample, update the m and c values. How we are updating the m and c values I will explain. You have to update the m and c values. Later take the second sample, again update the m and c values. Take the third sample and update the m and c values. Take the fourth sample, update the m and c values. Now one iteration is completed. One epoch is completed. Now take the second iteration. Once you go to the second iteration, again you have to start from the first sample and the second sample and the third sample and the fourth sample. After each sample you have to update your m and c. Then the second iteration is completed. Now go to the third iteration. Again it is starting from the first sample, update m and c. Second sample, update m and c. Third sample, update m and c. And fourth sample, update m and c. So this process will be repeated until how many epochs you have defined. Yesterday we discussed, right, number of epochs equal 10,000. Like that you have to define how many number of epochs, maximum number of iterations. Up to that time the iterative algorithm will be runs and m and c values will be updated. Suppose m and c values are reaches to its optimum point, then even though iterations are progress, that will be available at their point only, at the optimal point only. Fine. Hope you understand this aspect, stochastic gradient descent optimization. So in the stochastic gradient descent optimization, you have to remember one thing, that is, In stochastic gradient descent optimization technique, you have to initialize the model parameters, later pass the one sample at a time, update the model parameter, later pass the second sample, update the parameter, pass the third sample, update the parameter. Suppose if you have the 100 samples, you have to pass all 100 samples one by one, update the parameters. Then all the 100 samples are covered, then we can say that one iteration is completed. One iteration is completed. Right? So, one iteration is completed. So, if you take the 100 epochs, then you have to update the parameters, go to second iteration, third iteration, fourth iteration, like that. Friends, before going to our step-by-step procedure, I am asking one question, that is, suppose I am giving the problem. The problem is predict the electric load on a substation at a particular point based on the available load at the same time but the previous day, 24 hours back. So in order to do this forecasting problem, I want to use simple linear regression model. If you take the simple linear regression model, so how many model parameters are available? Anyone can tell, please? How many model parameters are available for a simple linear regression model?
2.
Only one, sir.
No.
Rmse.
In a simple linear regression model, how many
Only one.
model parameters are available? How many model parameters are available in a simple linear regression model?
Yes, sir.
How many?
Input.
How many model parameters? How many model parameters are available? So it is a 2. Your model parameters are M and C, right? Because you are going to estimate a value output based on one input, that is be using the line equation which has the parameters M and C. So this M and C are called as the model parameters. Right? So if you take any problem, if you think that forecasting problem can be attempted by using the simple linear regression model, then you have the 2 model parameters. One is the slope M and C is the y coordinate C. Right? 2 parameters. So 2 parameters. So you have to update the 2 parameters every time. If you consider the yesterday's problem, f of x equal to x square plus 5. So you have the only one decision variable. Here we have the 2 decision variables, 2 model parameters. If there is a 1 decision variable, you are updating one parameter, only updating one parameter. Whereas if there is a 2 variables, you have to update the 2 parameters. Here we have the 2 model parameters, you have to update the 2 model parameters M and C, and finally you have to identify the M and C values where the difference between the actual output value and predicted output value will be minimum. Right? Fine. Now my question is, so this is the problem I have given, and I asked that please write a code to learn the simple linear regression model for 100 iterations, whereas my data set has 100 samples, or let us do 10 samples. My data set has 10 samples. Understood? So I am giving a problem that maximum number of iterations that model will learn, that's equal to 100 iterations, and available data set containing the 10 samples, and the number of model parameters are 2. The 2 are M and C. Right? Now my question is, suppose you are running this algorithm. At end of the algorithm, how many times each model parameter, that means each model parameter and M and C will be updated over complete training process. My question is, over a complete training process, how many times each model parameter will update?
1000 times, sir.
Yes, perfect. So it is 1000 times because 100 into 10. Why? Because in one iteration, you have to take the first sample, update M. You have to take the second sample, update M. You have to take the third sample, update M. Fourth, update M. Fifth, update M. Like that, 10. So 10 times in one iteration, you are updating your model parameter 10 times. Because you have the 10 data sets. The samples in the data set is 10. This happens in the one iteration. If you go to the second iteration, same thing. Again, take the first sample, update M, second sample, update M, third sample, update M, fourth sample, update M, ninth sample, update M, 10th sample, update M. That is for second iteration. Like that, we are doing for the 100 iterations. In one iteration, your updations are 10 updates for one model parameter. Over 100 iterations, it will be the 10 into 100, that is 1000 updates will be happened for a model parameter M. Right? So why I am asking this question is, you have a visualization and how the model parameters will be updated. Right? For that purpose only I am giving small. I am asking this small question. Fine. Now we will discuss about. We are not going to the algorithm. We are not doing any numerical calculations. Now we will discuss about the algorithm. Later we will do some numerical problem. Later we will exercise the. We will do some exercises. First step 1. So you have to read your data set xia and yia, and you have to initialize the model parameters m, mx. I am just model parameters m with m equal to 1 and c equal to -1. See friends, all are gradient descent algorithm based approaches, whether it is a stochastic or mini batch or RMS crop, whatever it may be, all are coming from the roots of a gradient descent approach. So in the gradient descent approach, what is the hyperparameter? What is the parameter we are using additionally? That is called eta. So you have to use the eta value as 0.01. I am taking the 0.01. So what else I have to define? Anything else I have to define? Initialize. ఎవరైనా చెప్పగలరమ్మా? ఇంకా ఏ పారామీటర్ నేను ఇనిషియలైజ్ చేసి ఉంటుంది? వాట్ ద పారామీటర్ ఐ హ్యావ్ టు ఇనిషియలైజ్ అడిషనల్లీ? Random? Yeah, you have to generate this model parameters M and C randomly. You have to generate the model parameters M and C randomly. But for our demonstration purpose, I am taking the randomly generated values 1 and -1, like that I am taking. So while writing the code, you have to choose random values. You have to write random dot uniform, some value you have to generate for M and C values in code. But in the numerical calculation, I am taking some M equal to 1, C equal to -1 randomly. Eta is the 0.01. What else I have to define? What else I have to initialize?
Epochs.
Perfect. So you have to initialize the number of epochs. You have to initialize the number of epochs. Let us assume for it the numerical calculation, I am taking the only 2 epochs. Perfect. It's a perfect. Right? Almost all variables we have initialized. Now step 2. So what the step 2 is? Set iteration count iter equal to 1. Set iteration count iter equal to 1. That means first iteration is started. Step 3. Now tell me what may be. Just think what may be here, what I have to set. Let us assume I have a data set xia, because one input, one output, xia and yia. So I have some samples, some number of samples. Now what I have to do here? Any idea? Just think and give an answer. Okay, fine. As I said, in the first iteration, take the first sample, update M, second sample, update M, third sample, update M, fourth sample, update M, right? So you are initializing the iteration count. Now you have to take the sample 1. You have to take the sample I equal to 1. I am representing with I equal to 1, sample I equal to 1. So I equal to 1 means sample I equal to 1 means, so you are taking the input and output from the first sample. You are taking the first input and output from the first sample, right? Now step 3, what you have to do now is, so in this algorithm you have to find a gradient of your cost function or loss function with respect to the each decision variable. Why you are taking the gradient? Because see, the roots, as I said, the roots are coming from the gradient descent approach only. If you try to observe how the variable will be updated, x equal to x minus eta into dou f by dou x. So the gradient of a loss function or objective function with respect to the decision variable, that is the required. What type of gradient descent, what type of gradient optimization technique you have used, but that will be must. The name itself says that gradient. So you have to calculate the gradient. If there is only one variable, you are calculating the gradient of the function with respect to x. Yesterday we take the 1 hour example like 4x square plus 5y square plus 10 equal to something. Then we are calculating the gradient of that function with respect to x and with respect to y also. So in our case, what is the objective function? What is the objective function? In our case, what is the objective function? What is the objective function in our case? Now my problem is learning. Now I'm writing the learning algorithm for the simple linear regression model using the stochastic gradient descent optimization technique. As it is a gradient based optimization technique, I have to calculate gradient of your objective function. So what is the objective function in this problem? So what is the objective function in this problem? It is a half mean square error, right? Just in the previous case I have discussed half mean square error. That's equal to 1 by 2n sigma I equal to 1 to n yia minus m into xia minus c whole square. Fine. Now in case of stochastic gradient descent optimization technique, I told that you have to take only one sample at a time and update the parameter. Not all samples at a time. You have to take the one sample at a time, update the parameter, then the line moves toward that point. If you give the second point, then update the parameters, then your line moves somewhere between the first point and second point. Like that, m and c values will be updated. Now tell me friends, if I am writing a learning algorithm for the simple linear regression model using the stochastic gradient descent optimization technique, what modification I can expect here? Anyone can tell what modification I can expect here in the objective function? There is a slight modification I have to incorporate in case of stochastic gradient descent optimization, which take one sample at a time and it updates the model parameters. What correction that I have to do here? What correction I have to do here? Anyone are able to? Sorry, some of the people have given some information on the chat box. I am unable to see, friends. Sorry, I didn't see the chat box regularly because I am demonstrating the class only. At end I will see the questions. Yeah, someone answered also, right? Thank you. So, but I am unable to see. So, just orally, can you tell me what modification I have to do here in the objective function in case of the stochastic gradient descent optimization?
Only yia minus yip, sir.
Yeah, that's only. This is the yia, this is the yia, and this is the yip. Mxia minus c, mxia plus c is the yip. I'm telling, in stochastic gradient descent optimization algorithm, we have to take one sample at a time, update the parameter. That means you have to update the parameter based on the gradient. Gradient means you have to calculate the gradient with respect to the objective function, right? So you have to correlate all the statements. Then what may be the modification that I have to incorporate in the objective function?
So differentiation of that objective function.
No. See, I am taking the one sample at a time. I want to update the model parameter M and C. If I want to update the model parameter M and C, I have to calculate the gradient of an objective function, right? So if I want to calculate the gradient of an objective function, so in your objective function, do you have the sum of the errors of all the samples? The objective function, do you have the sum of the error for all the samples? No, right? Because you are taking the only one sample at a time. You are taking the only one sample at a time, right? So what that modification will be here is, in case of the stochastic gradient descent optimization algorithm, this n equal to 1. This n equal to 1. So slight modification here is, it is a 1 by 2 into I equal to 1 to 1. So no need to write anything. So yia minus m into xia minus c whole square. Because only one sample is available at that instant to update the parameter. Because we are passing the one sample at a time, we are updating. In case of the stochastic gradient descent optimization. So now it is called as a cost function, or we can call as a loss function, or we can call as a objective function. Now your objective function is readily available. Your loss function or cost function is available for the learning algorithm using the stochastic gradient descent optimization technique. Right? So now what you have to do? What I have to do now? First, in step 4, what I have to do? So I have to calculate gradients of your cost function or loss function or objective function with respect to the model parameters. So in the fourth step, you have to calculate gradient. Let us assume this I am calling as a f, loss function or objective function or cost function. So dou f by what will be here? Dou f by
Dou m.
yes, dou f by dou m, that's equal to once we are differentiating this equation with respect to m, this 2 will become forward, right? So now 2 will be cancelled. So we have yia minus mxia minus c. What else? We are differentiating this objective function with respect to the model parameter m. So now it is
Into minus
perfect.
xia.
Yes, perfect. Minus xia. So minus xia. That's it. So like that, you have to calculate the gradient of a loss function or cost function or objective function with respect to the model parameter m. That's equal to minus yia. This yia coming from your data set. M is coming from the initial value. Xia coming from the data set. C coming from the initial value. Xia coming from the data set. So all the values are available. You can easily calculate the gradient. Right? So that's the fine. Dou f by dou c. That's equal. So we have to find the gradient of a objective function or loss function with respect to the model parameter c. So what it will be? So that's equal to, again 2 come forward, 2 will be cancelled. We have yia minus m into xia minus c. What else I have to add?
Into minus 1.
Yes, it's a minus 1. That's it. So by using this equation 1 and equation 2, you have to calculate your gradient. So that is the fourth step. In a learning algorithm of a simple linear regression model using stochastic gradient descent optimization algorithm. So maybe today take more time because we are starting with linear regression model, but tomorrow it will not take that much time. We will start directly from the learning algorithm because we are discussing about the simple linear regression model here. So 1 and 2. In the step 4, we are calculating the gradients. So after calculating the gradients, in step 5, what we have to do? Anyone an idea? So based on the discussion in the yesterday's class, after calculating the gradient, what we have to do?
Update the value.
Perfect. So we have to update our model parameters. So how we update the model parameter? M equal to, because model parameter M, like yesterday we discussed x equal to x plus delta x, that's equal to x, delta x equal to minus eta dou f by dou x, right? So similarly here we have the M. Now tell me M equal to M minus eta into dou f by dou m, dou f by dou m at that initial values, dou f by dou m, right? Similarly you have to update C. So C equal to, so why I am getting minus 8 and everything we discussed yesterday. So most of the algorithms are roots are coming from the this gradient descent technique only. So slight modification. That's why yesterday I am focusing on the only gradient descent algorithm. So C equal to C minus eta into dou f by dou C. So like that you have to update your model parameters. You have to update your model parameters. Why you are getting this one? Yesterday we discussed continuously, right? So I'm not discussing again why I'm taking the M equal to M minus 8 into dou f dou m. We discussed yesterday all those things. Now step 5 is over. Now what will be the step 6? Now model parameters are updated, right? So once the model parameters are updated, now anyone can tell what will be the next step? We are updating the model parameters.
Compute the function. Compute the function.
No need here, because see I will we can compute the function also. Fine, we can compute the function also. But your learning algorithm will be number of lines will be increases. But here not required is during the learning algorithm we are continuously updating the parameter. We are continuously updating the parameter. ఎప్పటి వరకు మనం అప్డేట్ చేస్తుంటాం అప్ టు వాట్ వీ హ్యావ్ అప్డేట్ అంటిల్ వీ రీచెస్ ద మ్యాక్సిమం నెంబర్ ఆఫ్ ఇటరేషన్స్. Maximum of iterations. So after completing the maximum number of iterations, what are the readily available your model parameters, final model parameters M and C? You have to take that M and C. Now you can use predict, but using that M and C values, right? Fine. So no need to calculate. If you want, you can calculate, but not required, because the main goal of this learning is how you can update your parameters. Right? So what will be the step 6?
We go for next sample.
Perfect. So you have to go for next sample. So that's equal to I plus 1. You have to go for the next sample. That means second sample. Now go to step 7. So what here? Once you are updating the sample, then what you have to do? You have to check if the sample number less than or equal to ns. Ns is nothing but number of samples available in the data set. ns is the number of samples available in the data set. So if the current sample count, next sample count is less than number of samples available in the data set, then we have to go to which step? Anyone can analyze. Let's assume you are taking the first sample and you are updating the model parameter. You are updating the sample, that's I equal to I plus 1. Now you are going to second sample. So definitely second sample less than the available number of samples, 5 samples. So if this condition is true, then which step you have to go?
Fourth step.
Perfect. So you have to go to step 4. And calculate the gradient based on the second sample information, and also updated M and C values. And also based on the updated M and C values, and also data available from the second sample. If this condition is true, else means your next sample count is more than the number of samples available in the data set. Then what you have to do? You have to go to the next step. So next step means there is a step 8. Next step is a step 8. So what you have to do in the next step is we have to update the iteration now. You have to update iter equal to iter plus 1. Now we are updating your iteration count. Now once your iteration count is updated, then go to the step 9. In the step 9 you have to check for the convergence criteria, that is number of iterations. If number of iteration is less than or equal to number of epochs what you defined, number of epochs what you defined. So if it is a true, that means suppose if you are using the 2 samples, your iteration count is 2, so it is satisfied, right? So it is a true, then you have to go to which step?
Step 3, sir.
Perfect. You have to go to step 3. Perfect. Go to step 3, again you have to start from the first sample. Again you have to first start from the first sample. Perfect. Else you have to go to the next step. Go to next step, that is called 10th step. So in 10th step what you are doing is, so 10th step means, we are going to the 10th step means this is false condition. False condition means you are achieving the maximum number of iterations what you defined in the initial stage. That means if you define 100 epochs, you are reaching the 100 epochs. You are reaching the 100 epochs. If you define the 1000 epochs, you are reaching the 1000 epochs. If that condition is satisfied, so then go to the step 10. So in step 10 what you have to do is, that means you are closing the learning process because it reaches the maximum number of epochs how much you have defined. How much you have defined. So once it is closing, then last step what you will do is, you have to read or print the latest M and C values. That means what are the available M and C values in the last iteration, you have to take those iterations. You have to take those iterations. Sorry, take those parameters. Take those parameters. Right? I hope you understand, right? So these are the final model parameters that machine learning model learn. So model learn outundante, it will updating its parameters so that the mean distance between the actual value and predicted value are almost equal. Not exactly equal. If it's exactly equal, it's a great, but it's not possible especially in case of the regression models. That is possible only your data sample will be lies on a straight line. All the data samples available on a straight line, then only possible. But if that is the case, no need to go for this process also, because it's a simple line equation, y equal to mx plus c. Right. So M and C you have to choose. So after reading the M and C, you have to calculate errors. Errors, those errors called as mean square error and root mean square error and mean absolute error. So these errors you have to find. So these errors will help you how much accurate your model is, how much good your model is to predict the some load forecasting, whatever it may be. So the performance of your model, the training performance of your model is depending upon the, so you have to calculate these errors for the both training and testing data set also. So you have the thousands, suppose if you have 100 samples of data, you have to use some 90 samples of data for the learning, training, and you have to use that separate 10 samples of data for the testing. You have to test the model also, right? Okay, so like, okay, that will be another case, I will tell later in case of the NN. Okay, fine. So you have to find the MSE, RMSE and MAE on both training data set and training data set means the data set which is used for the training purpose. And there is separate data set we have to maintain to test that one, test that model, whether it is predicting properly or not. So on the data set also you have to calculate these 3 error matrices using these 2 model updated parameters, updated model parameters. Now how we calculate these 3 parameters I will discuss. How we calculate these 3 parameters I will discuss in the next board. Now let us assume a proper M and C values are available now. Your learning algorithm is completed. It reaches the whatever how many iterations you are defined, 100 or 10,000, whatever it may be. Now you are getting some value of M and some value of C. Now take the data set. So data set contains the X and Y, XIA and YIA. Now what you have to do is you have to calculate you have to predict the output based on the available input. Let us assume there are 4 samples. Let us assume there is available 4 samples. 4 samples, right? So what you have to do is already these actual values are available. Actual values are available. Now predicted values you have to calculate. How we can calculate the predicted value? So your regression model will be like this, right? So we have drawn already. Your regression model will be, your simple regression model will take the input XIA and multiply with the model parameter M, and that is added with another model parameter C, and it will give the predicted output YIP. So this is the black box which contains the model parameters M and C. So multiply m with the input and add c, it will give the output predicted. So YIP will be predicted as m into xia plus c. Now calculate the predicted output. Let us assume it is the y1a, y2a and y3a and y4a. Similarly, predicted values y1p, y2p, y3p and y4p. And how we calculate the error matrices MSE, Rmse and MAE, how we calculate? So that is calculated as, so MSE is calculated as 1 by number of samples in the training data set, sigma I equal to 1 to n, actual value YIA minus YIP whole square. N equal to 4 here, right? N equal to 4. YIA means it's coming from here. YIP means it's coming from here. So take the difference and square it and add. So that will give the mean square error. That's how we can calculate the mean square error. And how we calculate the root mean square error, Rmse, the simple square root of mean square error. That's called 1 by n sigma I equal to 1 to n YIA minus YIP whole square. And next one is a MAE, that's equal to mean absolute error, that's equal to mean absolute error, that's equal to 1 by n sigma I equal to 1 to n YIA minus YIP absolute value. That's it. So these are the three matrices. So this is for the training data set. You can do the testing data set also. Only these values will change. These values will be changed from the testing data set. Xi value and YIA value is available. So based on the available data, you have to compute predicted value and take the calculate the errors. If these errors are very less, that means so whose model has the less number of losses, there is a good model. So that based on the errors, we are evaluating the accuracy of the model, how the model is perfect, right? So this is the complete learning process of simple linear regression model. The complete learning process of the simple linear regression model using the stochastic gradient descent optimization algorithm. Stochastic gradient descent optimization algorithm, right? So friends, give me time. Now I will do the, so I am explaining the step-by-step procedure. Now I will explain the numerical calculation. For one epoch, because it's difficult for all epochs, right? So let us assume XIA, YIA, your data set. Let us assume your data set is 0.2, 3.4, 0.4, 4.6. Let us assume. Okay. Or do one thing. So we like this type of numbers. Simple way. 2, 6, 3, 6 plus 8. So let us assume your data set has the only 2 samples. So if X is input is 2, then your output will be 6. If your input is 3, then output will be 8. Output will be 8. Fine. So now I want to build a simple linear regression model which is able to predict the output Y based on the available input X. Based on the available input X. Now first of all I have to train the model. First of all I have to train the model based on this data set, based on this available samples. So what are doing in the step 1? In the first step, what we have to do here is, so you have to read the data set XIA and YIA. So as I said, today it will take this much time, but tomorrow it will not like this, because we no need to start from the simple linear regression model. What is simple linear regression model? How the weights are updated like that. So what else? You have to read eta, that's equal to 0.1. Let us do 0.1, and initial values of your m, that's equal to 1. It's your choice. 1 randomly generate. C equal to -1, and a number of epochs I am defining as 1. Number of epochs I am defining as 1. Step 2. So set iter count, iteration equal to 1. Step 3. Set sample I equal to 1. That means first sample. Step 4. So what we are doing in the step 4? we are calculating the gradient. We are calculating the gradient of a loss function or cost function for simple in regression model. That's the dou f by dou m, that's equal to, trying to recollect, that's equal to minus YIA. So what is the YIA? 6. YIA, that is 6. Minus M is the 1. So 1 into XIA, that is the 2. Minus C, it is the minus 1. So it is the plus 1 into 2. Because XIA equal to, right, into 2. So what it will be? 6 plus 1, 7. 7 minus 2, 5. 5 into 2, 10. It is the minus 10. Here minus is there, no? Minus 10. So you are calculating the gradient like this. And calculate dou f by dou c. That's equal to minus 8 minus 1 into, sorry. So what else here?
6
Yeah.
minus
6 minus 1 into 2 plus 1. This 2 will not come into picture now. So now it is a 5, minus 5. So you have the dou f by dou m and dou f by dou c. Now what is the step 4? Step 5. Step 5 is the updation of the parameter. Updation of the parameter is m equal to m, that's equal to 1, minus eta, that's equal to 0.1, eta, that's equal to 0.1, and dou f by dou m, right? Minus eta into dou f by dou m, that's equal to dou f by dou m equal to minus 10, right? So minus 10. So this will be 2. This is the 2, right? This is the 2. And c equal to c minus. So that means minus 1 minus eta 0.1 into dou f by dou c, that's equal to minus 5. So what it will be? Minus 1 minus into minus plus 0.5, that's equal to minus 0.5. Now the new m and c values are 2 and 0.5. Sorry, 2 and minus 0.5. Right? Now what is the step 6? What is the step 6? Step 6 ఏం చేస్తామా? In step 6, you have to update the sample count. I equal to I plus 1, that's equal to 1 plus 1, that's equal to 2. Now we are in the second sample. Then what you have to do? You have to check step 7. In the step 7, what you have to check? If your sample count is less than or equal to number of samples or not. So your sample count is 2. Less than or equal to, what is the NS value? Number of samples in the dataset, NS value?
2, sir.
2. So now it is satisfied, right? This condition is satisfied, true. So if condition is true, then you have to go to the step 4 again. You have to go to step 4 again, right? Now go to step 4. So once you go to step 4, I am writing again step 4. In the step 4, what you have to do? Again calculate the gradient. So dou f by dou m, that's equal to minus. ఇప్పుడు ఏమొస్తున్నాం ఇక్కడ? YIA.
Minus 8.
Yes, that is the 8 minus m. What is the m value? Is it 1? What is the m?
Minus 0.5.
2, sir.
2. Perfect. It is the new. You have to update. We are updating the value of m. So it is the 2. So 2 into x, that is the 3, minus c. C is the minus 0.5. So that will be plus 0.5. Right? Into 3. So what is the value here? Minus 8. 3 into 2, 6 plus 0.5 into 3, something. So you have to calculate. What it will be, maybe 0.5, right? 8 minus 6, 2, 2.5. 2.5 into 3 means it is a 7.5. I think it is a 7.5, right? So it is a minus 7.5. It's a minus 7.5. Similarly, you have to calculate the dou f by dou c. That's equal to, up to here it will be coming to picture, right? Up to here. That is the minus 8 minus 6 plus 0.5. So that's equal to, ఎంత వస్తుందమ్మా? Minus 2.5. Now the new values of, dou f by dou m equal to minus 7.5 and dou f by dou c equal to minus 2.5. So once we are calculating the gradients on the second sample, then we have to update now. Again, now step 4 to step 5 we have to go. In step 5, what we have to do here? M equal to m minus, what is the m value now? M minus kadamma, m value ఏమవుతుంది ఇక్కడ?
2, sir.
2. 2 minus 0.1, that's the eta, into dou f by dou m, that's equal to minus 7.5. So that's equal to ఎంత వస్తుందమ్మా 2 plus I think it's a 0.75. 2 plus 0.75. And c equal to what?
minus 0.5.
Here, na? It is minus 7.5, na?
M is 2.75, sir.
Intama?
M is 2.75, sir.
Yes, m is 2.78. C. For c case, what is the c value? C equal to c minus, minus 0.5 minus eta, eta into minus eta into 0.1 into dou f by dou c, that's equal to minus 2.5. Now this is the new m value and new c value, right? So initially you are taking the 1 and minus 1, later it is the 2 and minus 0.5, and here it is the 2.75 and something value here, m and c. Like that mod parameters will be updated. So later what we have to do, again go to the step 6. Now in step 6 what happened? I equal to I plus 1. Your current sample is 2, right? Yeah, 2 plus 1, that's equal to 3. Now check for the condition in the seventh step. What is the condition? So your sample count is 3 now, is less than or equal to number of samples 2. Is it true? It's false, right? So as it is a false, you have to go to the step 8. What is the step 8? So what is the step 8? In step 8 you have to update the iteration count. So iter equal to iter plus 1, that's equal to 1 plus 1, that's equal to 2. Now go to step 9. In step 9 what you have to do, you have to check for the iteration count. So if the iter value less than or equal to epochs or not. Your iter value 2 kadamma, less than or equal to number of epochs, how much they said? 2, 1. So it is a false case, right? 2 less than or equal to 1, it is a false. Then go to step 10, where step 10 you have to take the latest m and c values, and using that m and c values you can calculate the mean square error, root mean square error and mean absolute error on both training data set and also testing data set. You have to calculate. This is for the one iteration, so you have to run it for the multiple times. Hope the this complete calculations you have understood, I think, concept, what is the simple linear regression model, how stochastic gradient descent optimizer will update the model parameters, and with numerical calculations I have explained. See friends, you can implement a simple linear regression model by using some Python libraries, especially by using the scikit-learn. But most of the people are researchers and students, so my suggestion is we have to go from the some basics, what happened behind. Once you are in a project, in real-time projects, in application development, then no need to do complete code. Readily available codes are available. At least at that stage of learning stage, it's better to understand what happened behind, and you have to write your own code. Then it will increase your confidence on the algorithms, on the machine learning perspective, and also it will increase your logical thinking capabilities. So it's my suggestion actually. So I hope the complete theory convergence is completed. So now we will discuss the lab session. Right? So where is the lab session? Fine. So lab also. So next 20 minutes I will explain first lab, and you have to So you have to explore on the second exercise, and if you have any doubt, you can call me at any time during the morning session. Anytime you can call me. We will discuss if you are unable to understand. See, problem is, let's consider a sample data set have one input and one output. And number of samples are 4, 0.2, 3.4, 0.4, 3.8, 0.6, 4.2, 0.8, 4.6. Develop a simple linear regression model with one iteration, not one iteration. Actually, I am giving this exercise for my students to do the hand calculations. So you have to, as we are implementing in the Python, then you can use some 10,000 or 100 iterations. using the stochastic gradient optimizer. So see friends, you have to import a Python library called NumPy. That NumPy library is used to do the matrix operations in Python. Alias name is np. That means if you're not using the alias name np, then you can call some method by using numpy dot. If you use the alias name, then you can call np dot. Yesterday we calculated as mt.pow instead of math.pow. Similarly, you have to import math as empty, and you have to import random. So what is the purpose of random library here? So the main purpose of the random library importing is to randomly generate the initial value for your model parameters m and c. Model parameters m and c. Right? Fine. Now data. So now read the data. Data equal to, I want to read the data in the form of the matrix. So that's how we read the data. Data equal to np dot array, open the bracket, close the bracket, and again open the square bracket and close the square bracket. Inside, between the every square bracket there is a one row, like 0.2 3.4, 0.2 3.4, 0.4 3.8, 0.4 3.8, 0.6 4.2, 0.6 4.2, 0.8 4.6, 0.8 4.6. Like that you are creating a numpy array or a matrix, numpy matrix, and assign to a variable called data. So that is the data, our data containing the total 4 samples. Later, I am randomly generating a value. I am randomly generating, actually we have to generate the randomly. So otherwise I will remove it. Fine. So randomly generate m and c in between some range. I'm using some -1 to +1. You have to define some range, or you can choose some, as I said previously, 10 10 or whatever it may be. So you can randomly generate some value in the search space for m and c. It will update slowly. It will update, and later eta equal to 0.9. I am considered here eta equal to 0.9, and maximum number of iterations I have set, it is 10,000. So in the algorithm, what I said in step 1, you have to read the data set xia yia, and you have to initialize your model parameters m and c randomly, and you have to read your learning rate eta, and also you have to set your maximum number of epochs. That has happened here. And second cell, we are calculate the gradient of a loss function with respect to the each model parameter. So that is the so if you observe gradient of your loss function containing y value, x value, m value, c value, right? There is a y minus mx minus c into x. So it contains the y, m, x, m and c. So those parameters you have to pass m, c, x and y. Now the m derivative means dou f by dou m. That is a -1 into actual y minus mx minus c into x. C derivative equal to -1 into y minus mx minus c. And you have to return two derivatives. Because we have the two model parameters. You have to return two derivatives. Now your gradient approach. For iter in range maximum iteration. That means this outer loop will run for the 10,000 times, for the maximum iterations 10,000 times, right? And whereas inner loop, that is the for sample in range of length of data : 0. So data is if you observe, it is a matrix having the 4 rows and 2 columns, right? So here data : 0 means MATLAB, if you have idea in the MATLAB, you can easily understand what it will have. Data : 0 means it will extract all the rows from the 0th column, that means first column, because in the Python index will start from 0. In Python index will start from 0. 0 means first column, 1 means second column, because indexing starting from the 0. So you have to extract all the rows from the first column, that is the 0th index column. And length means how many number of elements available in that matrix, in that extraction. How many elements are available? The 4 elements are available. That 4 elements are 0.2, 0.4, 0.6 and 0.8. So 4 elements are available. 4 means why it is a 4? It is the total number of samples are 4. total number of samples are 4. So like that I am extracting the total number of samples. I am extracting the total number of samples. So that sample, this in the second loop will run for the 4 times because it has the 4 samples. Because length of this data will be 4. Now inside the per loop you have to find the gradient. Is the dou f by dou m. It will catch del underscore m catch the dou f by dou m. Del underscore c catch the dou l by dou c. Dou f by dou c. Now update here, that means step 4. In the step 4 we are calculating the gradients, right? It is the step 4. It is a step 4, right? So now go to step 5. In step 5 what we are doing? We are doing the updating the parameter. That's equal to m equal to m minus eta into dou f by dou m, c equal to c minus eta into dou f by dou c. That's it. That's over. Just simply 1, 2, 3, 4, 5 lines, and these are the 4 lines something. So almost all are less than 10 or 15 lines of code, right? So you can do this process using the scikit-learn libraries also for doing the simple linear regression model. But as a learner at the starting stage, it's better to start like this. Then when you develop the application, then you can go with the libraries, then better. So now we will execute all the 3 cells. Initialization, because of the net speed and everything, it will depends how much fast this will run. Now this gradient function is executed. Now complete running algorithm. Now it's running. Yeah, it's giving the values 1.999 something, right? 2, right? It is the 2 and 3. So final m value is, actually I have started with m some random value between -1 and 1, but it has landed at final m value is m equal to 2 and c equal to 3. So final m value is 2 and c value is 3. Now based on this m and c values, you are using the simple linear regression model to predict, right? So suppose if your input passing is 0.2, if your passing the input is 0.2, then anyone can tell what the predicted output by the simple linear regression model. Now what is the predicted output for the input 0.2? If I am giving a 0.2 as input to a trained simple linear regression model, what will be the output?
3.4, sir.
Perfect, right? Is the actual value, but predicted value is m equal to 2 and c equal to 3. So mx, that means 2 into 0.2, that is the 0.4, plus c, that is the 3. So 3.4. So this is the 3.4. Right? Because it is a small simple problem. So, and also pure linear, because to make you understand, I am taking a simple data. Hello? Sorry, I am not getting, please. Hello? 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 Right? So friends, only to make you understand, I am taking this data sample. If you observe data sample, these are the points are drawn from the y equal to mx plus c equation directly. That's why your line is passing through all the points. Your line is passing through all the points and you are getting a 0th error. But in the real time, don't expect that all the data points will be available on the same line. Definitely you will get some error. And moreover, for the non-linear complex applications, you won't get the right solution using the simple linear regression model. Right? Okay, fine. And you can go through it and also exercise. If you have any doubt, let me know. And now real-time exercise. Fine. Estimate bicarbonates of well water based on the pH value using the simple linear regression model and consider the stochastic gradient optimizer. Right? So do the manual calculations, not required for you. If you want, you can try later. This is the actual assignment. So I want the data set, right? So you can download the data set from the here, this link, groundwater dataset pH value and bicarbonates. You can click here. Where it is groundwater, yeah, here. Click on groundwater survey and download the data in the Excel format. Yeah, SLR09, SLR09. Fine, I am downloaded the dataset. Now dataset is available, friends. Now take this dataset into the Google Colab environment. Take this dataset into the Google Colab environment, because you are running the code in the Google Colab environment. It can't detect your data available in your local machine. You have to push the data into your Google Colab environment. So for that you have to click in this folder, and you can click in the upload button. Select the dataset. Dataset is available in the downloads. Fine, enter. So once I restart the session, this will be gone. Then you have to re-import again. So if to keep it every time, then we have to do some other things. You have to mount your Google Colab on your drive. So we will discuss later. Fine. So now import Pandas as a PD. Pandas is a library to do the data manipulation. Now df, that is a variable, equal to pd dot, you have to read the Excel data. So your Excel data is SLR09, right? So you have to rename it SLR09. What is doing is pd dot read Excel means it will read the data from the Excel and create as a data frame. Now df dot head means it will show the top 5 entries on your dataset. Total top 5 entries on your dataset. I will show the dataset now in Excel. Yeah, this is the dataset, right? 7.6, 57, 57. So this is the pH value and this is the bicarbonates values. One input, one output. So that df dot head will print the top 5 entries. Top 5 entries. So now I will run this code. Run it. It is the top 5 entries. 0th index, 1st, 2nd, 3rd and 4th. Next 1, 2, 3, 4, 5 entries. Right? Perfect. Next, in the machine learning, what you have to do is you have to do the normalization. Don't feed the data as it is. It will create two problems. One is if your data is a large numbers, it will throw a nan error, not a number error. And second thing is, in this case, simple linear regression model is okay. Suppose if you are building a machine learning model which feeds the multiple number of features and it is predicting some output. If the multiple number of features are at the different genre, different space, like let us assume I am giving I have a data set which contains the sex, that is the male or female. Another input feature is salary. So male and female, I am giving the 0 or 1. So that column containing the either 0 or 1, whereas the salary will be maybe in 10,000, 50,000 or 1 lakh. There is a large size, right? Then if you feed the data as it is, your model will be highly biased towards the large values. So then it's better to normalize the data. So normalize the data means you have to identify the maximum minimum values and you have to normalize it like this. So normalize the data. So df is the actual value minus minimum value divided by maximum value minus minimum value. So once you are doing the normalization, you are getting the values in the range of 0 to 1. All are normalized between the 0 and 1. The normalization was required. Well, while doing the numerical calculus, I am not explained actually. But if you go for the machine learning problems, you have to normalize the data. Whereas at the time of the prediction, you have to denormalize it again. Okay. Now, there is a library called scikit-learn library. From this library, I am taking scikit-learn framework. I am taking a library called train test spit. So train test split method, which is used to split your data. You have the x and y, right? You have the x and y, and you have split the data. Suppose if you have the 1000 entries or 100 entries, you have split the data into 90:10. Test size equal to 0.1 means, so 0.9 is the training size, 0.1 is the test size. That means 90% goes to the training data and 10% go to the testing data randomly. Understood? We have the 100 samples of data. Out of 100, 90 samples of data go to the training and 10 samples of data go to the testing. That has happened by using this cell, right? Yeah, I have to not define. Normalize x and y are not defined. Where it is? Yes. Where? I have to run this code. Now we have to run it. Perfect. So from here, rest is same. What happened? We are importing the numpy array, math array, randomly generate M and C values, eta value, maximum number of iterations. And here gradients. Same code. And this is the algorithm. So it runs for the 10,000 depots. So finally it shows m equal to minus 0.24 and c equal to 0.789. So finally it is stable at m equal to minus 0.24 and c equal to 0.89. Now m and c values are available now. Now what we have to do by using this m and c values, you have to calculate you have to predict your output based on the available data on training and testing. Later you have to calculate the mean square error and root mean square error. Now first of all you have to predict the data. To predict the data, what you have to do is, so this x train and y train and x test and y test are in the data frame. It's coming from here. X train, x test, y train and y test are in the data frame, not in a pure matrix. Now you have to convert into the array as a matrix. np.array of the data frame, it will convert into the matrix. Now what I am doing here is, so now for I in x train, so from the x train I am taking each x value and passing that x value into the mx plus c. Now I am predicting, and that predicted value I am assigning to this matrix, appending to that matrix. So finally this y-pred train contains the predicted output on the training data set. Similarly, it is for the testing from x test. It is from the testing data set. So you have to predict it from the testing data set. So see, for next all 10 classes we are using the same piece of code. So you go through this code once again. If you are not unable to understand, tomorrow we will do the same piece of code for the batch gradient descent optimization also. These codes will not change. What changes will, in case of the batch gradient descent optimization, this portion will change and this portion will change. So finally you have
So once explain 10th portion, sir.
10th, fine.
10th portion.
10th. This one? Nana, isn't?
Yes, sir.
Yeah, fine. So it's the
third, yes, sir. The third line.
Third line, this one, na? This third line, right?
Yes, sir.
Oh, perfect. Sorry. Yeah. So
Yes, sir.
yeah, it's the gradient. Is the dou f by dou m and dou f by dou c. That's equal to gradient of. For the gradient function, what you have to pass? M value, C value, X value and Y value. But X value, that is the X train, Y value in the Y train are in the data frame. You have to log the values. So to log the values, to extract the values from the data frame, you are using X train dot ilog sample. That means if sample equal to 1, so X train lo first value it will read. Similarly, ytrain dot ilog. See, the dot ilog is used to lock the value from the data frame. So which value you have to lock? You have to pass that value here. You have to 0th index or first index, whatever it may be, right? So that means for each sample, see, for a sample 0 to sample, how many samples are there? We have to extract sample by sample, right? So we are passing the sample 0. So 0 means first index, 0th index means first sample. So 0th index, from extrain you have to log that value. You have to take that value. Like it is the 0th index, right? So you have to extract this value, right? And similarly extract this value from the ytrain. Ytrain, extract that value, ilog. Nothing but it is the M and this is the C. So this is called X. You are taking the X value from the input and this is the Y value, this is the output. We are extracting. Why I am using the dot ilog? Because this extrain ytrain are the data frame model. So, and rest is similar. M equal to M minus eta into dou L by dou M, dou F by dou M, and C equal to C minus eta into dou F by dou C. Fine. So, see, as of my knowledge, I have written this code. I will tell you one thing. If you give one problem to one candidate, if you give one problem to the two candidates and ask them to write the code, even though they got the same solution at end of the code implementation, there may be a different approaches. So no need to follow this code only. So you can explore more, and if you are able to try to minimize the number of lines, it's very good. So now it's the M equal to M minus eta into dou F by dou M, and C equal to C minus dou F eta into dou F by dou C, like this, right? Now, so here I am calculating the Y predicted, that means the predicted output on the training data set and predicted output on the testing data set. Now I am calling the sklearn library and I am importing the mean squared error and root mean squared. You can write your own code also. In the demonstration I am giving the equations for the mean square error, root mean square error and mean absolute error. You can use the for loop and you can write that also. Okay, but I am directly calling the libraries for this case. So MSE mean square error is equal to, I think it is not mean square, it is Rmse, root mean square error. It is Rmse, root mean square error. That's equal to square root of mean squared error between ytrain and ypredict. This is the YIA. In our demonstration, it is like a YIA and it is like a YIP. And we are calling the YIA and YIP. So it will calculate the difference YIA minus YIP, make it square and divided by total number of samples and make it square root. That is happening here. And similarly, it is for mean square error. It is a mean square error. What happened here? Ytrain as YIA, it is the YIP. So once we pass these two values, what it is doing is, it's calculating YIA minus YIP whole square divided by total number of samples. Backend code. You can write your own code also. So print the mean square error. Similarly, mean absolute error. So mean absolute error. And pass the actual value and pass the predicted value. So what it gives? YIA minus YIP divided by sum and divided by total number of samples. So this is the complete procedure. This is on the training data set. And you have to same thing on the testing data set. Okay. So friends, it's almost 9 o'clock. So if you are free, just go through the code. If you have any doubt, you can call me tomorrow at any time. If you are unable to, tomorrow we will work on batch gradient descent optimization. Again, most of the code will be repeated. Then we will discuss in depth again. Okay, fine. So for today, I want to close this session. I hope you understand. In this session, we are discussing about the simple linear regression model and how stochastic gradient approach updates the model parameters M and C, and we did some laboratory exercises. So this lab link I already shared with you. On your free time, try to explore. Okay, tomorrow. And if you have any doubt, please call me. Otherwise, and tomorrow we will discuss about the batch gradient and use the most of the same code. We will discuss further in tomorrow. Okay. So I will stop the sharing. And thank you all. Actually, I thought I want to finish by 8:30. It's 9 o'clock. stop share. It's fine now. So if you want, you can leave now. Yeah, you can leave now and try it. And if you have any doubt, please let me know. So we will discuss later. Yeah, thank you all.